Hey, thank you for attending these sessions. So we are going to continue our discussion on continuity. We have discussed about example 6 on a polynomial. Particularly, we have also explained in the previous lecture why is that the rational polynomials is continuous. So this rational polynomial is continuous because first the polynomials is continuous. Then the theorem 9 quotient rules uh, guarantees that if f and g are continuous, then their ratio is also continuous. Therefore, we are able to state that the rational polynomials is continuous whenever it is defined. Now, this is another example. You have an absolute functions. So an absolute function is to be plotted. Now, when you talk about this absolute function, it must come to your mind straightforwardly within a flip of a second. The shape of the absolute function, it looks like this. Now, the shape of the absolute function is a very common functions. In general, when you study ZCA 110, mathematics or of calculus or any other mathematics, it is almost a mandatory requirement that you are able to know at the fingertips the shape of certain well-known function. For example, a linear function y equals to x, y equals to x squared, y is x cubed, sine function, cos function, theta function. The shape of this function would be best to know by heart. Now I know all these functions, the shape very easy. When you show me a graph, then sometimes I can easily guess what function is this graph referring to. Okay, so I would advise you that you should take note of the shape of those commonly defined function, right? So the absolute function is like this. It's defined to be the values of a function that's always positive. So then you ask the question whether this function is continuous or not. So the functions has a domain which goes from minus infinity to infinity. So throughout all the values of x which are in domain, in particularly at x equals to 0, the limit exists, and the values of the absolute function there are also the same as the values of the function at x equals to 0. Therefore, the absolute function is everywhere continuous within its domain. So is the trigonometric function cos and sine, right? Cos and sine is everywhere continuous within its domain. So it's tangent, right? So even though you look at the tangent function, I think it looks something like, I'm not sure, I think it looks something like this. Okay, I forgot exactly the tangent function, which I should know. So a tangent function at 0 is 0. So the tangent function, I think, looks something like this, right? Then there's a asymptote here. So this is a tangent function. So by definition, the tangent function is continuous throughout its domain. So this discontinuity is not lying in its domain. Therefore, the tangent function is still continuous. So in general, the cosinus function and sinus function and tangent functions, the basic trigonometric function is continuous. Okay, so we love continuous functions for many reasons. Okay, so then the next theorem we're going to talk about is a theorem that allows you again to easily predict the continuity of a new function, which is constructed out of two known functions at which their continuity property is known. Okay, so this is very similar again to theorem 9. Theorem 9, you can construct a new function by taking the sum of the two function f and g or difference, or multiply them, divide them, or raise them to a power. So you can, again, when we talk about the operations of function in the previous chapter, you can also form what we call a composite functions of g and f. So you define the composite function. So assume that you have a function f, and then the functions is continuous as c. Then at these values of c, you put it into the values of fc into g, and it so happened that the values of the function g at the point fc is also continuous, then the new function which is obtained with the composite function is also continuous. Okay, so that is a very useful theorem that allows you to deduce the continuity of any new function which is obtained by making a composition out of f and g. So you can immediately visualize these operations from this graph. So first of all, you start off with a point C, then here, then this C is fed into the first function here into f, then f that goes into the f will give you an fc. So this fc is in turn fed into g. So the g will take the values of the fc value into a new function, and the values of this new function is defined as g composed of f operated on c. So when you write down these statements, you have to have a clear idea in mind that the procedure of calculating this number comes in a stepwise manner. First, you start from a point x equals to c, which is the values on x, then this number goes into the function of c. As a result, you got fc, then fc is another number. This fc will goes into g, g will process f of c to give you a new number. So this is a new number which is written and expressed as g composed of c. So basically, I am explaining to you, when you write down these statements, you have the whole idea in your mind what is actually the exact procedure, right? It comes in step. First, you put C into F, then you put FC into G, right? So if you don't understand that, you just look at this formula and then just memorize it, you are not learning things correctly. Okay, so try to understand every single mathematical statements that you write down and explain to yourself what is actually happening within these statements. Okay, in generally when you study mathematics, you don't really do this, right? So I advise you, when you learn mathematics, try to interpret every single steps, every single statement that you write down. That helps you to understand the concept of mathematics more deeply, rather than just brute memorizing of formula. Okay. So assume that you have such a situations where the functions of f is continuous as c and the function of g is continuous at fc, then the new function of g composed of f is continuous fc. So this is what the theorem number 9 says, right? So this is another example that shows you. So for example, you look at a, right? So a is a function which is given as, let me take a look at my own slides. Okay, so we are looking at a function called square root of x squared over 2x minus 5. And we are asking the questions whether this function, let me call it the h, is this function continuous or it is not. So you can think of this or prove the continuity of this function in various ways. Either you apply theorem 9 or theorem 10 to prove this. So for example, you can prove the continuity of these statements using theorem 9. Now theorem 9 says what? Theorem 9 says that if you have let me dig out what theorem 9 says. The theorem 9 using the power law, it says that if f is continuous at a point, then when that function is raised to the power of r over s, the function is also continuous at that point. So you can use theorem 9 number 5 to prove these statements by showing that you have, say, a function of f, and this is equals to, say, a polynomial, right? So this is a polynomial of x squared minus 2x and 5. And then you said that this function is continuous for all, is continuous for all values, is continuous for all x, right? For all x within the real number set. So fx is continuous. Therefore, by the argument of theorem 9, if f is continuous at all points on x, and if this is raised to the power of half, then this new function is continuous due to the virtue of Theorem 9 power law, where here R is set to be 1 and S is set to be 2. So you prove the continuity of these very simple functions by using Theorem 9. Yeah, okay. So this is applications of Theorem 9 to prove the continuity of that function. Now you can also prove the continuity of the function fx as square root of x squared minus 2x minus 5 using Theorem 10. So Theorem 10 is slightly different. Theorem 10 means that you have to express h as a composite functions of, so you have to think of two composite functions. So for example, you think of f functions as a polynomial fx squared minus 2x minus 5, right? So this function is a polynomial. Then you define another function, gx, to be x raised to the power of half, right? So according to, well, not according, so you look at function f, function g. So function f is defined to be continuous throughout all values of x in the real part. So is equals to x, well, let me say that the domain of f and the domain of g is equals to all the real values within the negative infinity to infinity. It means that the function f is defined for all x, and g is also defined for all values of x. The range of the function f is also the same. The range of the function of f is also the same as minus infinity to positive infinity. Okay, this is the first statement. Then the next statement is that the function of fx is continuous for all values of x, and g of x is continuous for all number, right? Whatever number that you put into the argument of g, the function is also continuous. Therefore, you expect that the values of g, when you replace the argument to g by the argument of x, this composite function should also be continuous, because g of x is continuous for all real number of x. So the range of function f is in the real number, right? So all values of fx, the range of f is from minus infinity to positive infinity, and the domain of gx is also minus infinity to positive infinity. Therefore, it is quite obvious that g of f is also continuous. So we have argued and explained that the function of g, the function of g, which is x raised to a power of half, is continuous. The function of f, which is x squared minus 2x minus 5, is continuous. Therefore, you can compose f of g. The compose of g of x of g is just then equals to x squared minus 2x minus 5 raised to the power of half. Okay, so this is the original function we want to prove, right? The function of a is the square root of x squared minus 2x minus 5, and this is expressible in terms of g composed of f. Okay, and in previous explanation, we have argued that g is continuous for all x. G is also continuous for all the argument that is in the range of fx. Then this expression should also be continuous by the virtue of theorem number 10, right? So if f is continuous and g is continuous as f of c, then the composite is continuous. So I've just explained to you that these expressions of square root of x squared minus 2x minus 5 is expressible in terms of G composed of F, and then I argue that the functions of x squared minus 2x minus 5 raised to the power of half is continuous by the virtue of the theorem 10. Now you also can argue for the continuity of these functions by looking at the example of B. So let me come to this part and then explain to you again how you can argue that this function is continuous. So you can look at the explanation here. Well, this is a rational power of identity function. I think this is the application of theorem 9. So I think for this particular example B, the continuity of this function can be proven through theorem 9, which is to use the quotient theorem, but it is not, I think, easily proven using theorem 10. So for this example, we have proven the continuity of this using theorem 9 and theorem 10, but here I think you can't prove this using theorem 10, but you can prove this very easily using theorem 9 because this is a polynomial. This is also a polynomial. So polynomial raised to the power of 3 over half is also a continuous, and this denominator 1 plus 4 is also a polynomial which is continuous. Of two continuous polynomials itself is continuous. So you are asked to prove a statement of continuity, not through calculations, but through applications of theorem. And in the process of doing so, you have to explain in words and how you make use of the theorem, right? So these theorems are very powerful, right? You just apply it correctly. So these theorems allows you to come to very important conclusion. Now you do not know whether initially whether the functions is continuous or not, but using the theorem, you deduce the continuity of a new function that you never seen before. So you only see function A continuous, function B continuous. So when you make the new function out of two continuous function, then theorem 9 and theorem 10 allows you to deduce a continuity. So now we are talking about a new theorem, theorem 11, a theorem which is very useful in the context of root finding. Root finding is a very useful or very frequently encountered problem in mathematics. You have actually learned this already in your secondary school. So for example, if you have a function y equals to fx, you often want to find the solution to these equations. That is, you are asked to find out what is the values of the root of the function fxr. Now the root of the function is defined to be a value in the variable such that when you substitute the values of xr into the function, you get 0. Okay, this is called the root of a function. So we call it root finding. So to find the root of a function, you must first assure that the root exists. If the root doesn't exist, then you will not be able to obtain the values of the root, right? So in mathematics, you have to first prove the existence of something before you work out the exact values of that something. So the proof of existence is a preliminary requirement before you work out the details or the values of it, right? So always think of the proof of the existence to come before you work out the values of that quantity. So theorem 11 is going to be applied into the exercise of proving the existence or non-existence of a roots in a continuous function. So before we apply the theorem 11 in the context of root finding, first we have to explain to you what you mean by theorem 11. Theorem 11 is called the intermediate value theorem for continuous function. It is a theorem that applies only to continuous functions. So in this case, it just says this. It says if you have a function that is, say you have a x value here, and then you think of a function that is called fx and is continuous within some interval, say a to b, right? So then you define, since the function is continuous, so you can always define the values of fa, and you can define a values of f at b, right? And if the function is continuous, what you can do is you are quite confident that when you draw a line from the endpoint, then they would actually go continuously without some break in the between, right? So it's always possible to do this for a function that is continuous between a and b. If you draw the graph of the function, then the graph would not break somewhere in the middle or has a hole between them. So that is, by definitions, the very nature of a continuous function. So we are talking about a continuous function called fx, and fx is defined in this closed interval of a and b. So the theorem 11, it says that there must always a values that is called c, which lies between a and b, including a and b at the endpoint, such that the values of the function at the point c, we call it fc, is such that it is sandwiched between fa and fb. Okay, this is what the theorem says. It's like very simple. It's just like an example. Maybe say you can imagine that you have a person, your friend, like, so he has a head, and then he has a hand, and then he has a torso. Torso means the body, right? Then is hidden in some kind of partitions that you don't see. So maybe at the back of a banner, then you see the leg, right? So you see the leg, and then you know that your friend is still alive. Therefore, the torso and the leg, they are actually continuous, so they are connected. So as long as your friend are still alive and is still kicking, then you assume that the leg and the head are actually connected. So even though you don't see what is happening between at the back of the banner, then you know that for sure there must be something in the between, right? Somewhere in the between, something that is there. It's just that you don't see, but you are very, very sure that no, at the back of the banner, the torso is there. Okay, so this is sort of like an idea of the continuous, the intermediate value theorem. There must always be a point in the between of a and b where the values of the function f at c is sandwiched between f at b and f at b, such that the values of f at c, sometimes we call it y naught. Okay, so let me read out the theorem so that you can understand it in a more slowly manner. A function y equals fx that is continuous on a closed interval a and b takes on every value between fa and fb. So this is just the definition of a continuous function. In other words, if y naught is any value between fa and fb, then there must be some values of c where the function is defined as c for c lying in the open interval of fa and fb. So it just means that there must be a corresponding values of fc defined for values of c lying between a and b. Right? It's just a proof of the function defined at c. It's just a guarantee to be approved. Just like you see the head, you see the toe, then you are sure that there is something between them. Okay, so this is the idea of a theorem, intermediate theorem. So then you can try to see and apply this idea to these functions. You have a function that looks like this. This is actually a counterexample that shows that if the function is discontinuous but not continuous, then you don't always have a values of c that lies between the endpoint where the values of the function at c equals to a number that is lying continuously between f at the endpoint. Okay, so let's just try to apply this theorem to this example. Okay, so in this particular example, we have a sort of like a discontinuous function at the point x equals to 2. So let's just apply the intermediate value theorem. So let us look at the endpoint 1 and 4 and then write down the statements. So this is endpoint f a, this is endpoint b. Then it shows that according to the theorem, there must be number of c lying between 1 and 4 such that at this point c, the values of the function is lying between 1 and 4. So this statement should be true for all values lying between f1 and f4. Then we sort of like go and seek out the values of c. So here what is f at 1? F at 1 is a values of 0. So this is 0. And then what is f4? F at 4 is 3, right? So this is 3. So according to the theorem, it says that there must be always a number of the c where the values of the function fc lies between 0 and 3. So let us try to test out values that lies between 0 and 3. For example, let us say 2.5, right? So 2.5 is a number that lies between 0 and 3, right? 2.5 is a number that lies between 3 and 0. Okay, so this is a correct statement. So according to the theorem, there must be a values of c. Wait, there must be a values of c such that the functions evaluated at c must take on a values of 2.5 because 2.5 is lying between f at a and f at b, right? So the existence of c is guaranteed by the theorem. So can you now find a values of c such that the function at c is equals to 2.5 for this function? Is there any value where f at c is equals to 2.5? Which is the values of c that allows this to happen? The answer is, if you look at the definition of the function, no, you can't. You can't find any values of c where the c is restricted to between 1 and 4 only, right? So between 1 and 4, there's nowhere a value that allows you to have f equals to 2.5 because function at the function value at 2.5, which is this number 2.5, is not in the range of the function. Okay, so this is a counterexample. It shows that if there is a discontinuity in the function, then it is wrong to apply this theorem. So this is a sort of like counterexample to say that, to show you that if you apply these theorems into a function that is discontinuous at a certain point, then there will be some occasion where the you will lead to a wrong conclusion. No, the wrong conclusion is actually not really a wrong conclusion. It is just a result of you applying wrongly theorem 11, because theorem 11 is only applied to continuous function. So if you apply this to a discontinuous function, a function that has a discontinuity at the point, then you would arrive at the wrong conclusion. Okay, so it's a counterexample. However, if there is a function that is continuous, then you would always be able to prove that there must a point c. So this is an example to show, no, there is not guarantee to have a point c to fulfill this condition of fc lying between f at a and f at b. So it's an illustration of applying the theorem to a function that is discontinuous. So This is just illustration. Now, the important thing about the intermediate value theorem, as I mentioned, is its applications to a continuous functions when you find out a root. Okay, so this is just an explanation to this kind of situation. So imagine that you have a function f defined at a point A, where you have values of fa defined, and then you have a b, and then you have a function of fb defined. So you are quite sure that if you are talking about a roots, if you're talking about roots, the function that is continuous at the root must cut through the point from either positive to negative or from negative to positive, right? So if a root is ever to occur, then on the left hand side of the root and the right hand side of the root, their sign must be opposite to each other. So for example, here the left hand side of the root sign is negative, right hand side of the root the sign is positive. And for this particular case, the left hand side, the functions at the left hand side of the root is positive, the right hand side of the function at the root is negative. Therefore, if you have a root, then on the left hand side of the root, let's say you call it a, right hand side you call it b, then the values of the function at the left hand side of the root and the right hand side of the root, they must be opposite to each other. So this is a mathematical statement that describes this situation. That is, the sign of a function on the both sides of a root must be opposite to each other. Okay, so this is the sort of like the characteristics of a root. So this is what this slide is trying to tell you. So by applying this idea, the properties of a root into so what you do is that you apply theorem 10, theorem 11 into a function, a continuous function that has a root. So what you would like to do is that you apply this. So let's see how you apply this theorem. So if you have a function that has a root somewhere here and you do not know what exactly the root is, it doesn't matter. But generally you have a point fa, and then you check out what is the values of the function at the point fa, and then you look another point called b, and then you check the sign of the function at b. If the sign of a and b are opposite to each other, like in this case the fa has a negative sign, fb has a positive sign, then it's like this. Then according to the intermediate value theorem, it says that there must exist somewhere of C between A and B, such that the values of FC exists and it must lie between FA and FB for all values of that lies between FA and FB. So that means if you start B, say FB is somewhere here, FA is here, then you draw a continuous line. There must be somewhere that the functions f cross from negative to positive. Okay, so the values where you cross from negative to positive is the values of b of 0, right? So there must be a number that is like this. So this is a number that is guaranteed to exist, that lies between A and B. So here, imagine that this is negative and this is positive. Then when you go from negative side to the positive side, there must be a point where your y naught is just equals to 0, right? So if this is negative, this is positive, then somewhere in the middle, you must cross the 0 border, right? So there must be an values of the function at the 0 border such that the values of the function at this point is just equals to the value. So it means that there must exist a values of C between these 2 points such that function at C is 0, because 0 lies between F and B and F between A. Okay, for this particular example. So if you have a situation that is like this, right? So if it's like this, where you have FA and you have FB here, so this is B, This is FB. Okay. Then when you go from here to here, there must be a point C that lies between A and B, such that FC is always between positive FA. Say if this is equals to 10, and then this is equals to, say for example, this is say -1, right? So there must be always all values must be a values of FC that is lying between between 10 and -1, and then here you choose the values of FC to be 0, right? So 0 is lying between 10 and 1 as well. So the theorem guarantees the existence of FC such that FC is a number which is chosen to be 0. Okay, so 0 is lying between FA and FB. So it guarantees the existence of the roots. Okay, so this is an example. So if you have this function f(x) equals to x minus cos x, then you are asked to prove there is at least one solution or one roots for this function. So what you do is that, first of all, you always try to find out a trial number of FA and a trial number B. You work out the values of function at A and B such that their signs are opposite to each other. It doesn't really matter what number of A and B is, as long as you can find two numbers where they are negative to each other. So for example, if you have fx equals to x minus cos x, so just simply choose a number. So what number you should say? For example, you choose, don't know what, say equals to pi over 2. Okay, so f of pi over 2 is pi over 2. I think this is difficult. Cos of 90 degree, cos of 90 is 1. So this is a number. Then you choose another number. Don't know what number is that. So maybe you choose a number called minus pi over 2. Is it a good number? Minus pi over 2 minus cos of pi over 2. Cos of negative pi over 2 is what? Is also 1. Am I right? Is it correct? Okay, so cos of pi over 2. Let me try to figure out myself first before I proceed on. So cos of minus pi over 2 is equals to, so this is the pi over 2 CAST. So I think this is positive. So I think this is equals to cos of 90. Cos of 90 is 0. Okay, so I think cos of 90 is 0. So I'm sorry about that. So here cos of 90 is 0. So this is also 0. Okay, so hopefully that what I deduce here is correct. Cos of 90 is 0. Yeah, okay, so cos of negative 90 is also 0. So here you find out that f at pi over 2 is a positive number, which is pi over 2, whereas f at negative 90 is a negative number. Okay, so let me try to sketch these situations for this function onto a graph. I'm just going to sketch 2 points. So you have a pi over 2, and then you have a pi minus pi over 2, and then the values of the pi over 2 is this here, which is a positive number. It doesn't really matter what number is that, it's pi over 2. And then over the other side at pi minus pi over 2, the values is negative pi. So the values of f pi over 2 is somewhere here in the negative, right? So this is a negative pi over 2. So let me wrap off everything and now do this over again. So we have a situation of negative pi over 2 and pi over 2 where the values of the functions at negative pi over 2 is negative. And then the values of pi over 2 here is a number which is positive. So according to the theorem, then there must exist a values of c between minus pi over 2 and pi over 2 such that the values of the function at c is equals to 0. So that proves the existence of a root. To be more correct, this theorem only says that there exists at least one values of c between minus pi over 2 and pi over 2 where the root is equals is in existence. So in actual fact, for this kind of function, you may have more than one roots in general. So in order to know whether you have a roots or not, how many roots of that is actually beyond the guarantee or beyond the theorem. Now the theorem only guarantees the existence of at least one root between the two endpoints that you choose. So in this example, A is chosen to be 0, now B is chosen as pi over 2, but in the example I shown you, I choose A to be minus pi over 2, and I choose B to be pi over 2. So whatever value you choose as A and B, as long as you compare their sign between them, and if the sign is opposite, then you are very sure that in the between of the two functions, say here, you have negative, you have positive, then you could have at least one point where the roots is found. You could have also possibility multiple roots, right? So the theorem just say at least one. So you could have a situation where you have a situation like this, where you have more than one roots. So I think this is not correct. You could have more than one roots like this. So you go from here to here, then it cross 1, 2, 3, 4. So here you have 3 roots. It is also possible to have a different scenario where you have negative sign, positive sign at two endpoints. The sign at the two endpoints to be opposite, and you have only one roots, right? So at least there's one roots. When you go from bottom positive to negative or negative to positive, you must cross at least the roots or x-axis at least once. So in this case, you cross it 1 time, 2 times, 3 times. So this is the applications of the applications of intermediary theorem to root finding. Okay, so in general, if you look at the exercise, you are given some functions and you are asked to prove that you have a functions given to you, and you are asked to prove that at least exists one root between them. So I think I have also written a mathematical code to illustrate the applications of root finding. So that's all for this part of the lecture. So thank you for your attention.